Okay, this page is one of the extra papers that I gave you. This is not in your notes packet, so this should be in the little stack of papers that you got earlier this week. So we want to talk about derivatives and polar equations. So if I have a polar equation that's r equals f of theta, when I take that derivative, I'm finding dr d theta. That is not the slope. Dr d theta is comparing the rate of change of the radius as the value of theta changes. So what that's going to tell us is like as theta is changing, r is moving closer or further from the pole. That's what dr d theta would tell us is it's like the rate of change of the radius over rotations of theta. That's not the slope. Slope is a rectangular construct. So anytime we're talking about the slope, as it has been with everything else we've done, slope is going to be dy dx. So how do we find dy dx given that we have an equation in terms of r and theta? Well, the parametric form of a polar equation, we've seen this relationship before. X is equal to r cosine theta and y is equal to r sine theta. So if you have some equation, r equals f of theta, then it would be whatever your equation for r is times the cosine, and then whatever your equation for r is times the sine. That's going to give you your parametric form of x and y. Once you have the parametric form, then you can find the derivative of x with respect to theta, the derivative of y with respect to theta. And so dy dx is going to be dy d theta divided by dx d theta, just the way it is with parametrics when it's in terms of t. Okay, so our first job is to convert to parametric form. Then we can use dy d theta to figure that out. Okay, wherever dy d theta is equal to 0, that is where you have a horizontal tangent. Wherever dx d theta is equal to 0, that's where we have a vertical tangent. But if both are equal to 0, that's an indeterminate form. You can't make any conclusions about that. So we're going to look at just two examples. There's no homework on this until we get to some of the AP practice. So you can just continue working on your other assignments for tonight after we go through these examples. So first, we want to find the slope of the line tangent to r at the given value of theta. So we have this equation, r equals 3 times 1 minus the cosine of theta, and we have our value of theta is pi halves. First thing we have to do is write this in parametric form. So we want x is going to be equal to r, which we know is 3 times 1 minus the cosine of theta, times cosine theta. Again, this is r, that was the equation we had, cosine theta, that's the rule. So that's why we're multiplying by this extra cosine theta. So if we clean this up a little bit, we're going to get 3 cosine times 1, so that's 3 cosine theta, and then 3 cosine times negative cosine theta, so that's minus 3 cosine squared theta. Okay, so now we need the derivative, dx d theta. So that's going to be negative 3 sine theta. Now we need to use the chain rule here. So this is negative 3 times cosine squared theta. When we use the chain rule, this is going to be 2 times the cosine of theta times the derivative of cosine of theta. So this all together comes out to negative 3 sine theta plus 6 cosine theta sine theta. So there is dx d theta. Now, in a similar fashion, we need to find our parametric form of y, which is going to be, again, r times 1 minus the cosine of theta times this times sine of theta. Okay, so we get 3 sine theta minus 3 sine theta cosine theta. This one's not lovely because we do have to do a product rule over here. So dy d theta is going to be 3 cosine theta minus 3 times, so 3 times the derivative of sine, that's going to be cosine. So 3 cosine squared theta. We're subtracting all of this. And then we have plus 3 times the derivative of cosine is actually going to be negative sine times sine. So this will be minus 3 sine squared theta. Okay, so all together, this is 3 cosine theta minus 3 cosine squared theta plus 3 sine squared theta. That is dy d theta. And because we're going to plug in pi halves, we don't really need to worry about doing a lot of simplifying or anything like that, because we're just going to go ahead and evaluate this. So what we need, and we can shorthand our notation a little bit here, we need dy d theta at theta equals pi halves divided by dx d theta at theta equals pi halves. All right, dy d theta first. It's going to be the one on the right-hand side. The cosine of pi halves is 0. So that gives us 0 minus 0 plus sine of pi halves is 1. So this is going to be 3 over dx d theta. Now we're in the one on the left. Sine of pi halves is 1. So that's going to be negative 3 plus this is going to work out to 0. So 3 divided by negative 3, we get negative 1 for the slope of the tangent line at pi halves. It's a lot of work, but it's all stuff that we know how to do. Okay, example 2, similarly, if we want to find horizontal and vertical tangent lines, we need to start the exact same way. This one comes out a little bit nicer. We don't have quite as much going on. So x is going to be equal to r, which is sine of theta, times the cosine of theta. And y is going to be equal to r, which is sine of theta, times sine theta. So this ends up being sine squared theta. Also notice that we only want values from 0 to pi, which is nice. Okay, go ahead and do your derivatives here. Now, we don't actually need dy dx. We just need dx d theta and dy d theta so that we can set them equal to 0. So pause your video and see if you can take those derivatives, and then we're going to set them equal to 0. Okay, these are the derivatives that you should have. Now, wherever dx d theta is equal to 0, this is where we are going to have vertical tangent lines, because that's the denominator of dy dx. Dx d theta is what you divide by. So this is going to be where our vertical tangent lines come from. Now you could do this a couple of different ways. You may recognize that as a formula for cosine 2 theta. If you don't, that's okay. What I went ahead and did is substituted 1 minus sine squared theta for cosine squared theta minus sine squared theta again. So we get 1 minus 2 sine squared theta. Solve for sine squared, and we get positive 1/2 equals sine squared theta. And when we square root both sides, we get plus or minus 1 over the square root of 2 for the sine of theta. Now, 1 over the square root of 2, you may not recognize right away, but if you rationalize that, that is the square root of 2 over 2. So pi fourths is the first value for theta, but it's anywhere that it's positive, anywhere that it's negative, and again, only from 0 to pi. So that's going to be pi fourths and 3 pi fourths. These are our vertical tangent lines. Now we need to do the same thing for horizontal. So we set this equal to 0. And there's not much we can do with this other than the fact you may recognize that this is sine of 2 theta. If you don't, that's okay. If sine times cosine has to equal 0, that means either sine of theta equals 0 or cosine of theta equals 0. The 2 is kind of irrelevant. Where does the sine equal 0? 0 and pi. So we want both of those. 0 and pi, and then cosine is equal to 0 at pi halves and 3 pi halves. 3 pi halves is too big, so we just also want pi halves, and these are our horizontal tangents. Okay, So that's a little bit of a rundown with derivatives. We're going to practice this a lot more with some different activities over the next few days. But that is all you need to know for now.